Hi everybody, welcome to another video in Calculus 1, section 3.7, the chain rule. This is the most important section of Calculus 1. Before we actually go to the derivative part of it, the chain rule, we just need to review the function decomposition and the function computation. So, the way we combine two functions, we denote f little circle g, or we say f of g of x is a function inside another function. And of course the domain of the computation is the set of all the numbers x in the domain of g such that g of x is in the domain of f. Right. Now, let's see how it works. So fine. Suppose the function f of x is equal to 5x minus 1, g of x is equal to 3x squared minus 2x. What is f of g of 1? So we'll rewrite this as f of g of 1. And then we'll do it inside the parentheses g of 1 first. G of 1, of course, I'm going to put 1 in for x of the g function. Put 1 in for x. And that's 3 minus 1 is just 1. And then we go back to the problem f of g of 1. G of 1 is equal to 1. So this is just f of g of 1 is equal to 1. And we just do f of 1, which is 5 times 1 minus 1. 5 minus 1 is 4. Right. And then we write what is g of f of x. We'll rewrite this as g of f of x. And f of x inside is 5x minus 1. And so we'll just do g of 5x minus 1, meaning we're going to substitute this in for every x of the problem. So we have 3. Instead of x, we can put the parentheses. So in general, that's what the function g is. And now inside of the function g is 5x minus 1, so we put 5x minus 1 on each of them. Right, so that's what we have. Now, that's nice and all, but it's not as important as the decomposition, meaning here we have two functions, we combine, we compose, and we add into one function. Now, that's not as important as the reverse process, meaning that when we have one function, we're going to decompose that into two functions. So let's say we have h of x is equal to that. How do we decompose it? So the way to decompose this is first, just ignore what inside of the square root. Doesn't matter what it is. This function we can say is, or I just write a function of, say, a box. Doesn't matter what inside of that. And the box happens to be x squared plus 1. Yeah. So in that process, doesn't matter what inside first, that we have the square root function. After that, inside the square root is 3x squared plus 1. So put together we have two functions. The f is the outside function, g is the inside function. So we can say f of x is the square root of x. And then g of x is the second function. So that way we decompose h into f of g of x. Apparently, in order to do the chain rule, this process is the most important, kind of like half of the problem. The rest is the derivative, where the rules I post over there. Right. Now sine cube of x. Sine cube of x, actually the cube is evaluated right after we do sine x first. So instead, it should be sine x cube like that. Once again, doesn't matter what inside, we have a cube. So I can say we have a cube, something cube. That is the outer function. The inner function is sine x, so the box is equal to sine x. And then we can say the outer function is a cube, and the inner function is sine x. And then when we do f of g of x, we're going to get exactly that. So it's easy enough. Just pick up. It doesn't matter what inside we start with a function. Usually I just draw a box, cube, and then the box is equal to negative 3x to the fourth minus 2. In that case, we have the outer function is a cube, and the inner function like that. Simple enough. And then same thing here. That is secant of something, and that something is 3x minus 2. So we have the outer function. The first function is secant of x, and the inner function, or the inside, is 3x minus 2. Right. So in order to do chain rule, we have to know how the function compose together. We have to write like this. But in this case we have both of them are x, so usually it's not very easy to see as this. So usually we introduce a new variable. So suppose, now this is the chain rule. Suppose y equal to f of u, the function of u, and u is a function of and u is equal to g of x. So this is redundant. I will delete this on the note on my, yeah. Oh, no, never mind. That makes sense. It is differentiable at u equal to g of x. All right. That's not wrong. That's perfectly fine there. And u is equal to g of x. This is what I want to emphasize. So y is a function of u, and u is a function of x. All right. That's one point. Of course, the function should be differentiable because we'll take the derivative. And then we write f y as f of g of x, which is exactly what we have there. And its derivative can be expressed as this: derivative of y with respect to x is derivative of y with respect to u, and then derivative of u with respect to x, or we write like this. And then of course I could put the chain rule over there, but I didn't, because the chain rule is so important that we don't even need to know the formula. We just need to see how it works. So pretty much the idea here is derivative of the computation is derivative of the outer function multiplied by derivative of the inner function. Right, let's see how it works. By the way, here we write both of them x, but it will be easier if we use a different variable. You will see. Right, so find the derivative of y equal to 2x plus 4 to the 5th power. So first, y equal to 2x plus 4 to the 5th power. So if we want to decompose this into two functions, we're going to have something to the 5th, and then that something is 2x plus 4. So I will write something to the 5th, and that something is 2x plus 4. Right. and then we can label them anything we want. Let's say u. So in that case, y equal to 2x plus 4 to the fifth, decompose into u to the fifth, where u is equal to 2x plus 4. And then the derivative. We just need to take derivative of the outer function, which gives us 5u to the fifth, and then derivative of the inner function, which is 2. And then multiply them together, we have 10u to the fourth power, and u is 2x plus 4, so we substitute back in for u. That's what we have. So that is the derivative using the chain rule. Right. By the way, let's leave the other half because this is nice and all, but when we get used to the chain rule, we will use a little more compact notation. So when we use the more compact notation, I will write the solution on this side of the page. Right. So next, I'll find the derivative of the following function. So first of all, this is to the 7th power. We don't want to multiply it out. We can, but that will take a lot of work. And if we have the problem, let's say similar to this, 7.5. In that case, we won't be able to multiply it out. So the point here is don't multiply it out. Use the chain rule instead. So the chain rule says, first of all, ignore what inside and decompose it into two functions. So I will decompose this into two functions. Say a box to the 7th power, and then the box, doesn't matter what inside of, it's still the box to the 7th power, and then we have negative 3x plus 2 is the box. Now let's label that something. We can label both of them u. Right. Now we have two functions. Then we just take derivative of each one of them. First derivative of u to the 7th power is equal to 7 u to the 6th power, right? That derivative of u to the 7th power. And then we take derivative of this with respect to x, derivative of this with respect to x, of course, it's negative 3. Of course, if we write like that, that's really confusing. It's not subtracting, but it is multiplying too. And chain rule says we multiply those two derivatives. So that gives us negative 21 u to the 6th power. And finally, original problem, there's no u, there's only x. So we substitute back, u is equal to negative 3x plus 2. So that gives us negative 21 of negative 3x plus 2 to the 6th power. Simple enough, right? Once again, later on we will write the notation a little more compact. We don't need to substitute u and order, so we're gonna write the solution more compact. Right. Let's do one more with the u like this. So once again, we have the square root of something. Of course, we'll let that equal to u for sure. But usually when we have the square root, it would be better if we write that as power 1/2, because later on we used the power rule. That would be a little more convenient. The box is x squared plus 1. So now let's decompose that. We have a box to the 1/2, and then the box itself is x squared plus 1. Right. Now let's label the box something. and then we'll take the derivative of each one of them. First derivative of this is 1/2 u to negative 1/2, and derivative of this is a function of x is 2x. So put the parentheses around it and we multiply. Right, 1/2 u to negative 1/2 times 2 times x, so all of them are multiplied, right? All of them are multiplied. So in that case, I can put the 2x in front. If this is just one term, I can just put the 2x in front. Or we have 1/2 times 2x u to the negative 1/2, and 1/2 times 2, so this cancel out. 2. So we have x and u to the negative 1/2, and finally the answer must be in terms of x. So u is equal to x squared plus 1. So that we have as the answer. Right. So it's not that bad, right? Right. Let's do one more time using the box thing. Obviously, if this is the case, we can let the whole denominator equal to a box. So I have 1 over something, and that something is that. So we can just write, we have 1 over a box, and the box is equal to negative 5x cubed minus 3x plus 4. In that case, we can decompose a function into 2, right? Now, of course, we can label them u. Right, of course, take derivative of that, easy. Now we just need to take derivative of this. It would be easier if we write 1 over u as u to the negative 1. Because when we take derivative as a power rule, that will be easier, right? And then so we have the first one is u to negative 1, the second one is that. Now we use the chain rule. So derivative of this is negative 1 u to negative 2, right? Take the negative 1 power down, original power minus 1. And then we'll take the derivative of this function. Derivative of this is negative, take 3 down, negative 15 x squared, and then minus 3. Right, now, unlike the previous one, when we have one term, we can go ahead and move in front of. Most importantly, we can simplify. When there are two terms like this, don't do anything. Don't try to remove the parentheses. We can just leave it like that. Except just one tiny little thing. We can actually just multiply the negative 1 into this. If we multiply the negative 1 into this, we will have, we can move that in front. Yes, but like I said, we usually don't simplify anything. So we have negative 1 or just negative sign. The 1 looks silly. Move that in front. Usually we don't have to, but in this case, usually if we just substitute back into u, that is the derivative, and we're done. But in this case, because the negative can distribute into that and make it positive 15x squared plus 3, and then u is that and we don't need to simplify now. So again, distribute the minus sign. So that's how we do derivative using the chain rule. Decompose the function into two, take the derivative of each one, and then multiply together. And the rest is just cosmetic, trying to simplify. So when we have negative and negative like this, we can take the negative, distribute it inside. But that's all. We don't need to move this in front or keep it at the back. It doesn't matter. It's still just two functions multiplied together, right? So that's how we do the derivative using the chain rule. Now we will shorten the notation a little bit, make it more compact, because technically if you write a math problem like this, and especially an old school way, then probably don't like this. So we do that, the more it look more like math problem. It is without all of those marking here, right? So I just mentioned that on the previous problem. We'll go back and do that differently using a shorter compact problem, right? So this is the way I do it using the chain rule. Of course, this just will help us to visualize the problem. For the first few problems, we need to do it like that. But when we get used to, we don't need to do it like that. So let me just write the problem out. Y equal to 2x plus 4 to the 5th. Right, this is how the way I do it. So I will take derivative. Now the first thing is we have to know how to decompose the function. Of course we can do it like that, but like I said, when we get used to it, we can shorten the notation. Once again, it doesn't matter what inside of the parentheses, or I just say the parentheses. I'm going to put something to emphasize that it is going to be the parentheses. So I have the parentheses to the 5th power, right? So the derivative of that, regardless of whatever inside the parentheses, is not important. The derivative of that is going to be just the derivative of the outer function equal to the derivative of the inside function. So we can just write like this case. We will write it's going to be derivative of y with respect to u and u with respect to x. So we say y prime of u and u prime of x. Of course, this should be in term of x as well. Sorry, that is not. Yeah, it's really like this. But the point is, we have the derivative on the outside, then derivative of the inside. Yeah, because y is the function of x written like this. So write like that. It's not wrong, but this is more confusing. So back to our problem. So we have something to the 5th power. Derivative of that, I'll just ignore what inside the parentheses. Now I just consider the parentheses as a variable. So the derivative of that is 5 times the parentheses to the 4th, and then the derivative of the parentheses. Well, and then we have the 2x plus 4 inside the parentheses. Right, now we see this to the 4th power, and there's no more derivative. We're done with the derivative here, except we only need to take care of that derivative. So we'll have 5 to x plus 4 to the 4th, and derivative of 2x plus 4 with respect to x is 2. And finally, this is just a constant 2 multiplied to 5, and then multiply to that. 2 times 5 is 10. So 2x plus 4 to the 4th. A good practice of this is, so I consider a parenthesis, it's just a variable. So think about this. It's a good practice if we do the problem like this. Let's say we have y is equal, I do another problem, negative 2x plus 1 cube. Just let's do that. Right? So in that case, I can say just If it is the smiley face cube, then the derivative of that is going to be 3 times the smiley face, and then the derivative of the smiley face. So doesn't matter what it is. So this time I treat the whole parentheses as the one variable, and then take the derivative of that. If this is the smiley face with the cube, there will be 3 times the smiley face. But the chain rule, the only thing different in the chain rule, we have to take the derivative of whatever it is. If it is not x, if it is the function of x, we have to multiply by the derivative of it. So that is how I do derivative using the chain rule. But when we get used, we don't need to write that in different color like this. Right. Now let's do this problem again. Right, first, y equal to negative 3x plus 2 to the 7th power. Right. Once again, ignore what inside. Doesn't matter. Just put the parentheses around it. So what is derivative of the parentheses to the 7? Right. Derivative the parentheses to the 7. Consider that is a variable or something. That will be 7 times that to the 6. Right. Derivative. And then derivative of that. Yeah. So in this case, the derivative is the function of the parentheses, so we will have 7 times the parentheses to the 6th power. Yes, if the parentheses is a variable. If we treat the parentheses as a variable, that's what we have. And then the chain rule say we have to take the derivative of the parentheses if inside the parentheses is something as a function of x. So now inside is negative 3x plus 2, negative 3x plus 2. Right. Yeah. In this case, we don't need to write different variables. So that gives us 7 negative 3x plus 2 to the 6. And the derivative of this is negative 2x plus 2, so negative 3. And the negative 3 does not raise to any power. The 7 does not raise into any power. So this is very important. At this stage, you cannot multiply 7 to this factor because we have the 6th power here. We can only multiply together if they does not raise to any, if they do not raise to any power. So like 7 by itself, negative 3 by itself, raised to the 1st power. So both of them raise to the same power, then we can multiply. That gives us negative 21, negative 3x plus 2 to the 6th power. Right. Simple enough, right? Next, we have f of x equal to square root of x squared plus 1. And as usual, if we see that, I prefer to write this as x squared plus 1 to the 1/2, because y is the power 1/2. It's a lot easier than to take derivative than with the square root. So I will take derivative. So there will be a parentheses to the 1/2. So put the parentheses around it. Ignore what inside. Derivative is going to be 1/2. That parentheses 1/2 minus 1 is negative 1/2. So that is the derivative of the parentheses as a function. And then the chain rule say we have to multiply by the derivative of the parentheses. So in that case, x squared plus 1 inside the parentheses, and then we have 1/2 x squared plus 1 negative 1/2. Derivative of the parentheses. Right after this step, we just need to take derivative inside, which is 2x. And finally, this raised to negative 1/2, we cannot multiply this inside this negative 1/2. We can only multiply them if they raise to the same power. So the 1/2 here raised to the first power, the 2x here raised to the first power. In that the case, we can multiply them. So 1/2 times 2x gives us x, and then we have x squared plus 1 to negative 1/2. Right. So, like I said, if you want, that's correct, that's the answer. But if you want to, you can bring down x squared plus 1 to the bottom. Turn to positive power. And finally, the 1/2 power, you can write that as square root of x squared plus 1. Yeah, so if you want to, you can write the answer like that. But once again, derivative up to this point is good enough. Right, next example. Y equal to 1 over negative 5x cubed minus 3x plus 4. Of course, we can take derivative like that for the whole denominator. 1 over something. But usually, if we have the reciprocal function, I prefer to write this as negative 5x cubed minus 3x plus 4 to negative 1. Because negative 1 is easy power. Easy power to take down the reciprocal function. Right. Now, what inside is not important. Just have a parentheses. Yeah. Inside is a function of x. So the derivative doesn't matter what inside the parentheses. We're just going to say derivative of something, a parentheses to negative 1 is negative the parentheses original power minus 1. That gives us minus 2. So that is derivative of the parentheses. It's a function, as a variable. If we treat the parentheses as a variable, that's what we have. And then chain rule say we have to take derivative of the parentheses itself. Right. And the parentheses is negative 5x cubed minus 3x plus 4. 5x cubed minus 3x plus 4. Right. And we don't do anything with this now. We only need to do the derivative after that. Derivative of this is negative 15x squared minus 3. Once again, we only multiply things that have the same power. This one has the negative 2 power, so we not mess anything. Do not bring anything inside if it has the different power. This one negative by itself, so we assume the power 1. This also power 1. So those two things have the same power. We can multiply together. If they don't have the same power, do not bring anything inside. Do not multiply anything inside that. So negative multiply negative, that gives us 15x squared. Negative times negative, that plus 3. And so we have negative 5x cubed, negative 3x plus 4 to negative 2 power. And if we don't want to have the negative exponent, we can always bring it down and turn to positive. So that negative 2 power, move the whole thing down. the top will be 15 x squared plus 3, right? Yeah. So if you can see the function decomposition, then we can take derivative using the chain rule easily. Right, next. Now, that's the reason I refer to shorten the notation rather than write like this. Write like this, easy to visualize, but when we have a more complicated problem, that might not be as helpful. So the point here is just we have the square root of something plus 3x, right? So notice, very important, if you see the problem, the 3x does not belong to the square root. So that's why I wanted to write this like this, as opposed to that. We already did square root of x squared plus 1, right? Which is that, or any of this. We just need to take the derivative of 3x and add them together, right? Now, but of course, rather than do it like that, now we just want to put them together like this. So before we do anything, the square root, usually if we have square root, cube root, or reciprocal function like this, I just write that as a power instead. So we write that as a power 1/2. And then plus 3x. Right, so that is the function. We'll rewrite that as 1/2 power, so it's easier to take derivative. Now we will take derivative. Right. Once again, assume that is the parentheses. And we have that. So derivative of the parentheses to the 1/2 is 1/2 of the parentheses. Original power 1/2 minus 1 is minus 1/2. And chain rule say take derivative of the parentheses also. So that take care of the parentheses to the 1/2. What is the derivative of 3x? Well, that is easy. We don't need any chain rule for that. It's just 3. Yeah, derivative of 3x, just 3. Now inside the parentheses is x squared plus 1. Yeah. So we could potentially do a bunch of derivative, and each one of them are chain rule, and then we just apply like this. And the rest of the problem should be easy. Derivative of x squared plus 1 is 2x. And once again, this one has the power of negative 1/2. We do not mess with it. The 2x to the first power and 1/2. Both of them raised to the first power. So we multiply together. 1/2 times 2x is x. And then plus 3. Right, so we take the derivative of this. So that's pretty much derivative of that plus the derivative of 3x, which is 3, and we add them together. So it's simple enough, right? And then we say, how about when we have some trig function? Of course, we're going to have that too. So find the derivative for this function, right? So sine cube x. Of course, when you get used to it, you don't need to rewrite it. But we say sine cube of x and sine of x cube. You see the difference of those two, right? Of course, the 3 here goes with x, the 3 here goes with the sine. So in that case, on this one, we have to rewrite this as sine of x and then cube. So the cube is going to the whole sine x when we write like that. When we write like this, we only mean the cube is only applied to the x. So there are two different things. Right. So in terms of derivative, what are the difference? So let's take derivative. derivative of something cube, ignore what inside something cube is going to be 3 times the parentheses square, right? If we treat a parentheses as a variable, and then chain rule says multiply by derivative of the parentheses. Yeah, so that's the chain rule. Doesn't matter what inside of the parentheses. If it is a function of x, that's what we write like that. Right. Now we have sine x, and then sine x. Of course, the 3 sine square, we're done with derivative. This doesn't have any derivative in it, so that's good. We don't do anything with it, except if we want to. Never mind, just leave it like that. We'll write that in the next step though. Take care of it later. Right, what is derivative of sine x? Well, over there it says derivative of sine x is cosine x. Right. Now, once again, this to the first power and the 3 to the first power, we can multiply together. The square do not mess up with the sign because this raised to the second power. So we can say 3 cosine x, and then sine x square. But usually we don't write sine of x square like this. Just like this, the power, we just need to write in the sign, right? It's just cosmetic. But it is better to write sine of x square like that. Of course, you can just write, you can also write a 3 sine square x sine square cosine. Yeah, that's perfectly fine too. Don't even need to write the multiply if it is clear to understand. Then we just write like that. So when we write the power right next to a trig function, that means we take the trig function first and then we raise that power. So same thing here and same thing there. The next one is different. The next one is when we have sine and the parentheses is around the x cubed. It doesn't matter though. Derivative of something with the parentheses, assume parentheses is a variable. We take the derivative. It's going to be derivative of sine of something, right? Derivative of sine is cosine of the parentheses, and then chain rule says derivative of the parentheses. If the parentheses contain x in it, meaning a function of x, it's always like that. Doesn't matter what inside of it. Inside of it though is x cubed. Now cosine of x cubed, we already take care of that, so there's no derivative in it. And then x cubed, derivative of x cubed is 3x squared. Right. Once again, the x cubed, we do not mess with the x cubed because we have the cosine of x cubed. We cannot multiply the 3x squared with x cubed here because this to the first power and this one inside the cosine. So we cannot multiply them at all. So we can just leave the answer like this. However, it's just cosmetic. If the 3x squared like this, we can write in front. So I don't need to write the parentheses. When we move the 3x squared in front, we don't need to write the parentheses, and this is clear to the context. Yeah, it's just cosmetic, but that's all we do, really. So it doesn't matter what inside of the parentheses, we treat that as a variable. Treat the parentheses as a variable, take the derivative. And then chain rule says, and then derivative of whatever the parentheses is. Right, so that's what we have. Right, same thing on the next one. something cube, derivative of something cube, derivative of something cube, is 3 times that to the second power, and then derivative of the parentheses. That's what the chain rule is. Right? Now inside the parentheses is tangent x plus 4 and once again we're done with the derivative. Here we only need to take derivative of tangent x plus 4 again to the second power, so we're not going to mess with that. Derivative of tangent, once again over there, derivative of tangent is secant square, and derivative of 4 is derivative constant is 0, so that's what we have. You can put the parentheses here if you want to. Yeah, but like I said, usually for the cosmetic reason, if you want to write that in the similar term, so we can just remove the parentheses, or we can put the secant square in front in here, or leave it at the back. It doesn't matter. We can just say the answer is this. Yeah. Or we just put the secant square in front. It doesn't matter at all. Yeah. Usually it looks better if we have something to the power that we don't have anything after that. So as mentioned before, this to the first power, this to the first power, we can multiply them together. The square cannot mess up with that because different power, we cannot just bring something inside of that. Right? Next, we have this. Derivative of secant of something. So we'll take derivative. Derivative of secant is what? Over there is a secant and tangent, right? So we have secant of something, tangent of something, and then chain rule says derivative of that. Right. So first we have derivative of the parentheses as a variable, and then derivative of the parentheses. Inside of that, 5 sine x minus 1. Right, and of course there's no more derivative, only the 5 sine x minus 1 has the derivative, so we only need to take derivative of the last one. So I rewrite everything else. And then derivative of 5 sine x. Derivative of sine x is cosine x, which 5, so it will be 5 cosine x. And then derivative of minus 1, a constant, derivative is 0. So that's what we have. As always, usually if we have the last term raised to the first power, we try to avoid the parentheses. We don't need to write the parentheses, but if we write something like, for example, tangent of 5 sine x minus 1, and then we write 5 cosine x, usually when we don't have the constant by itself like this, if there's a constant, we write that in front. So like I said, it's just cosmetic. We put the 5 cosine x in front. In that case, we don't need any parentheses here. The constant usually stay in front, the number stay in front, and then the rest I just copy it. So just cosmetic. If the last one to the first power, I might just write that term in front, so I don't need to write the parentheses. That's all. Just like this, write that in front, so we don't need to write the parentheses around it. Right. Yeah. So that's the chain rule. Of course, we will do more example. I did mention that this is the most important section of Calculus 1 because all the derivative we have over there, it just apply to like sine x, cosine x. What happens if we have sine of 5x or something more than that? So more often than not, the derivative involve the chain rule in it. I mean, many of our problems will have to deal with the chain rule. Right, more example. Right, now, derivative of that. Once again, there's something in the parentheses, so derivative of the parentheses, doesn't matter what inside, that is the first step we do. So that is derivative of parentheses square, so that's going to be 2 times the parentheses to the first power. Or just that, yeah. The parentheses square derivative is 2 times the parentheses, and then we take the derivative of the parentheses. That's what the chain rule is about. Right, inside that it is t and 2t plus 3. So t and 2t plus 3. We already take the derivative of it, so that is good. Just going to leave it like that. Now just take derivative of this. Now the derivative of this is the chain, a quotient rule, right? This is a quotient. So the quotient rule, u prime v minus uv prime over v squared. In this case, u is t and v, the bottom, 2t plus 3. Take derivative. Derivative of t is 1. Derivative of v is 2. Alright. Then we have t and 2t plus 3. Right. Now, derivative of this, we're going to use the quotient rule. U prime v u prime v minus u v prime over v square. Right. Just keep it like that. On the top we will have 2t plus 3 minus 2t. The bottom is 2t plus 3 square. Usually in the chain rule, in the quotient rule, we don't multiply now the denominator. We just leave it like that. Right. Now, you get the point about the cosmetic reason. Usually, if it is to the first power, we don't need to write the parentheses, right? To just write like that. Don't need the parentheses here. But that's just a product. 2t minus 2t, so we just have 3. And then we have 2t plus 3 square at the bottom. Now, multiply fraction, all of them to the first power. That's why we can just remove the parentheses. Now, multiply them. By the way, whatever you do, we cannot cancel the 2 like this. In fact, in this, what we do is just multiply because that number in front we multiply to the top, so we multiply 2 to t to 3, 2 times t times 3, it's going to be 6t on the top. The bottom, 2t plus 3 square times 2t plus 3 to the first power. So that gives us 2t plus 3 cubed. Yeah, so that's why we don't multiply down the denominator, because sometimes there's something to simplify. Right, so of course, we might have a chain rule, including the product rule and the quotient rule. So the chain rule allows us to do a lot derivative of a bunch of different type of function. I mean, if we just have those derivatives, there's not much we can do, but with the chain rule, allow us to do derivative of a lot of things. Right. Next, derivative of sine of something. Derivative of sine of something is cosine of something. Doesn't matter what inside, but chain rule says multiply by the derivative of that. That's what we start with. Now inside is cosine of x squared. We already taken care of the derivative, so we do not do anything with this. This is done. We still have derivative here though, so it's not done. We have to take care of, have to do derivative here. But in front of that, we have cosine of cosine x squared. We're not going to do anything with that. Now just take derivative. Now we have cosine of x squared. So by the way, is that cosine of x squared or cosine of x squared? And you say no, those two are different, right? Because cosine of x squared meaning cosine like that. Yeah. So this one cosine of x squared. In fact, it's going to be, you put another parentheses around this. Now we focus on derivative of that. Derivative of cosine of something. Now ignore what inside of the parentheses. Derivative of cosine is negative sine of something, and then derivative of the inside. Doesn't matter what it is. By the way, this is still multiplied to it, so we better write the parentheses. So derivative of cosine of something is negative sine of something, and then derivative of that inside happen to be x squared. So we'll have cosine of cosine x squared times negative sine of x squared. Yeah, all of that has no derivative in it. We're done. Now just take derivative of x squared, which is 2x. So what we see here is, and this one, what we have is a chain rule inside of a chain rule, and there, I guess that is the reason we call that the chain rule, because in reality we have the change of the function. So we have the box inside the box, a parentheses inside the parentheses inside the parentheses. In which case, just do it from outside back in, and just, if we don't know how to take derivative of something, just put the parentheses around it and then just keep going. So we have that. Once again, cosine and cosine x squared inside the cosine. We're not going to mess anything with this because that belongs to the cosine. Likewise, if it has any power, we cannot mess with that. This though, to the first power, right? So we have the 2x multiplied with this. Again, x squared is inside the sine, so we not mess with that. But the minus side though, 2x and the minus together, raise the first power. Cosmetic reason, it's better to just write negative 2 in front. Oh, the x, negative 2x in front. If we write like that, we don't have to write a bunch of parentheses. and the minus in front is a lot better than the minus in the middle with the multiply. Usually when we say like 3 times negative 2x like this, is that better to write just negative 6x, right? Same reason. Negative 2x, it's better just write the negative 2x in front of that. Or we let's just use better example, like sine of x squared, let's say negative negative 2x sine of x squared, and then we have 5x cubed, for example. When we see something like this, the x squared here belong to the sine x, so we're not going to mess with this. We're not going to mess with the sine x squared. This to the first power and this to the first power, we can combine them so that we don't need to write the parentheses. So that negative 10 x to the fourth sine of x squared. So when we write like this, we don't need that parentheses and the negative in front, so that look better, right? So once again, that negative raised to first power, the 2x raised to first power, so we can combine them. The x squared inside sine x cannot mess with it. The cosine x squared inside the cosine x cannot mess with that. Bottom line is we just have cosine of x squared and then sine of x squared. As you see, when we write like this, we do not need the parentheses and the minus in front, the negative in front. Look a lot better than the product with the negative in the middle, right? Besides, positive times negative is negative, so that's why we write the negative in front. Right. Next, we have that. Usually when we have the power of trig function, we write everything in Sine. Let's use the bracket this time. Yeah, I will write just like that. Just put the parentheses here to emphasize that. Right. So once again, if we have the power to trig function, we write that as a power. Yeah, I put in the parentheses so we can see it like that. So we have a bracket cube. We have 3 times square. So the derivative of something cube is 3 times that thing square. Chain rule say derivative of that. Right. Inside the bracket, sine of 7x squared minus 3 right, I'm just going to write this back. Now, derivative of this. Right, so we take derivative of this with involving sine of a parentheses. Derivative of sine of something is going to be cosine and then derivative of that thing. If we don't want to confuse, it is the product multiplied to it. 7x squared minus 3, 7x squared minus 3. Right? By the way, when we write the power like this, we can put the power here, right? Just like the power here, move back into right on the top of the trig function. So we say 3 sine square. When we write like that, we don't need the bracket. That would be better, right? If we don't want to get rid of the bracket of the whole trig function, put the power right on the top of the trig function, right? This to the first power, we really don't need the parentheses. Unless there's a minus here, then yeah, I put the parentheses there. But yeah, it's not wrong, just keep it. And then derivative of 7x squared minus 3, that's 14x. Now just cosmetic reason, remove all the parentheses, as much as parentheses as we want to simplify the problem. First, this to the first power, so we really don't need the parentheses, right? We don't need this set of parentheses. We can just say it, 7x squared minus 3, and then 14x. Now, 7x squared minus 3 inside the sign, inside the square, so we're not going to mess with that, definitely. Don't multiply the 3 in front in the here, because they're inside different power. 7x squared minus 3 also inside the cosine, so cannot multiply the 3 inside, cannot multiply the 14x inside either, because this belongs to the cosine, and this belongs to the sine, which is inside the square. So we're not going to mess with any of that. What we can combine though, this to the first power, and this to the first power. Combine those two together. So we don't need to write the parentheses, and it looks better. 3 times 14, that's 42. And then we have sine squared, 7x squared minus 3, and then cosine, 7x squared minus 3. Yeah. So right like that, we don't need that bracket. We only bring the 2 inside, so we don't need that bracket. And we multiply this together, so we don't need the parentheses there. It's just cosmetic. We can only combine them if it raised to the same power. If it belongs to different power or belonging to a trig function, do not mess with it. Right. And next problem, just a little concept. How do we take the derivative of the computation given only the values where we don't have the function? Right, so we have that little table. So first, what is h of 1? H of 1, the function h is f of g of x. So we're going to take f of g of x and then 1, because we're going to take the derivative of that. A chain rule say we have to take, it's just the parentheses again. So derivative of that is derivative of the function f and then derivative of inside. Inside is going to be g of 1. Right. If we write like that, it'll be a little confusing, because you set g of 1, derivative of g of 1, it is a constant, and derivative of constant is equal to 0. So write like that is, it's not right. It is rather confusing. So don't write like that, because that is just a constant. So what we do instead, just leave that in x. And then we say it, after that, we say at x equal to 1. Right, we take the derivative of the function first, and then put 1 into it. So we're just going to give an x here. Yeah. So now we can put 1 in. Derivative of g of 1. By the way, derivative of this, if I rewrite, it should be like this. Derivative in front of g, so that's that's the way it should work, like this. So when we just look for g of 1. So what is g of 1? G of 1 is the values of function g when x equal to 1. When x equal to 1, g of 1 is equal to 2. So this is 2. And then we still have derivative of f at 2. G prime of 1. Derivative when x equal to 1 is 3. And next, f prime of 2. Derivative of f at 2 is 7. Right, so we have 7 times 3 is 21. Yeah, g prime of x derivative is just going to put derivative in here, and then we put 1 in it. Yeah. I'm not going to do the other problem because in that case we just set up the same thing. So actually I'm just going to write the beginning of it. So h of x is equal to f of g of x. So derivative of that is derivative g of x times derivative of x. And after that we will let x equal to 2. Yeah, and I'll let you do that problem. Yes, then we put 2 in all of the x's, and then the rest just follow what we have on the table. Alright, so of course that's the chain rule. The derivative of that's why I said I didn't even put the chain rule in the formula over there, because the chain rule is more like the concept. It is a combination of all of the derivative we have over there. So usually I put the parentheses around it, take derivative with the parentheses as the variable, and then chain rule says multiply by derivative of the parentheses. That's actually the way I do it. Yeah. So, and we practice a lot of this chain rule problems. So, I end this section here. As always, thank you for watching. See you in another video in Calculus 1.